everyone, this is your favorite chemistry instructor Mukta from Exam Essentials. Welcome to another video. Today we are going to discuss October 2024 Unit 4 Section A. So without further ado, let's start. An ester structure is shown. This said which pair of reactants would form this ester under suitable conditions. Now listen up, you can see very clearly that we should remember that from the for producing an ester, an alcohol and an acyl halide is required. Now for an alcohol, from the alcohol group, the H group will get away from the alcohol group, and from the acyl halide group, the halide group will go away. The halide group will go away. So this will basically cause, as they basically go away, the remaining intermediates add together and produce the final product, which is an ester. So in this case, this basically makes A and B irrelevant. So the only thing that we have left is B and D. Now obviously we need to check out the number of carbons in the left side. We have 1 2 3 4. There are 4 carbons, and we know the acyl, because why did I say 4 carbons on the left side? Because, and for this to happen, as we know that acyl chloride tends to contain the functional group of COX, where there is a double bond with oxygen. So we are already considering that the left side is constituted or taken away from the acyl halide group. So in this case, whatever the halide is, we need to check out the acyl group right here. So butanoyl is the correct option, because we can see there are four carbon groups. So the answer will be B right here. The other part will obviously be alcohol. In this case, it will be propanol. So the answer is B. So move on to the next one. It says that which compound will have the highest boiling temperature. Now we always remember two things, that the compounds that tend to have highest boiling temperatures are aldehydes, ketone, and this is our basically the priority group of aldehydes, which is carboxylic acids. Carboxylic acids tend to have a higher boiling point compared to aldehydes. And then we have ketone right here. Okay, so in this case we can easily say that the only carboxylic acid here is CH3CH2COH, propanoic acid. So the answer is D. Next one, it says the steroid nandrolone has the structure shown. This is the nandrolone structure. So they're basically saying how many chiral centers is there. If I talk about this, then if you count the dots right here, this is a chiral center, because we can clearly see that there are 4 different groups attached. Then there is a chiral center here as well, because we can see 4 different groups attached with it. Then we see another chiral center right here, which is obviously there are 4 different groups. You can see this group, this group, this group, and there is a hydrogen group attached. Then we have another group right here, which also consists of 4 different groups attached, while the other one is this one, and there is another one right here. You can see very clearly that both these carbon consist of 4 different groups attached to each of their 4 bonds. So that's it. So we basically have 6 bonds, so 6 chiral center is basically the correct answer to this one. Then they say nandrolone is broken down in the body into the compound as shown. You can see that. Now they said what reactions have taken place to form the new bonds at position 1 and position 2. Okay, fine. In case of position 1, if I talk about position, what reactions have taken place to form the new bonds at position 1? In case of position 1, we all know that in order to produce an alcohol, reduction is required, and in position 2 we can see that there is the production of carbon to carbon single bond. So it's only possible by the addition by an addition reaction. So since if that's the case, then we can easily substitute. There is no the options which basically consist of substitution reactions as one of the options. So B and C are irrelevant, so B and D are either one of the answer. Now we need to check out. We definitely know that alcohol is basically produced by the reduction of certain reactants by the help of reducing agents such as LiAlH4. So whatever it is, it must be produced by reductions. The answer will be B. Anyways, let's move on to the next one. We have C, a sample containing 2 times 10 to the power minus 9 gram per cm cube of nandrolone was analyzed using gas chromatography. The chromatogram produced is shown. You have the absorption and then you have the retention time right here. A second sample containing 4 times 10 to the power minus 9 was also analyzed using gas chromatography under the same conditions. Now they were answering that which is the chromatogram produced by this second sample. Now you can see very clearly that the sample previously taken and now which has been taken analyzed, which has been taken to be analyzed, is now double of the previous one. If it's double of the previous one, then we can already see whatever the sample is. You should always remember one thing, that is the retention time actually does not change. Okay, because one thing that you should understand, that is of course one thing, the only thing, the retention time actually does not change whatever the sample we take in gas chromatography. The only thing that's going to change is that the absorption is going to become double. For example, if it's here, if it's somewhere here, then it's like 1 2 3 4 5. It's going to be 1 2 3 4 5 6 7 8 9 10. It's going to be somewhere here. So the absorption becomes double since the sample has doubled, but the retention time, or in other words the detection time, remains the same. So we can say in this case we can easily see that three of these options are representing a change in the retention time. Only one is C and D. In C and D we can see that only in D the absorption has been doubled, but in C we can see the retention time is okay, but the absorption has not doubled. This basically is just a carbon copy of the given graph right here. So the only answer is D. Okay, so now let's move on to the next one. Titration curve for the titration with acid, with a strong base is provided. Now this type of graphs we know is provided only when basically there is when we basically take it as, when we take the acid as diprotic, when the nature of the acid is diprotic. So if that's the case, diprotic basically means that there are two dissociation of H plus ions. So in this case the only thing is possible is C, H2X, because two times the equivalence point has been reached. You can see it very clearly right here and here. And let's move on to the next one. Ethanoic acid can react with hydrogen sulfide ion. We have HSO3 minus very carefully, which is a correct acid conjugate base pair for this reaction. Now if I talk about this one, correct acid base pair, the ethanoic acid is reacting. So the acid will obviously be is reacting with an hydrogen sulfide HSO3 minus. So the acid is obviously CH3CO minus. So A and B is already cut. So among the C and D, we need to check out which one is the correct answer. Okay, now when it reacts, when CH3COOH reacts, what happens is that an oxygen is taken away from HS1. One oxygen is basically the H plus basically happens what? It happens to dissociate. For example, it happens to be something like this: CH3COO minus plus H plus. So the conjugate, and it is basically coming from where? It is basically coming from CH3 as it dissociates to reach an equilibrium position. So this is the acid, so the conjugate base will be this one right here, C3CO minus. The only possible option is C, as we can see very clearly, the stated in the below reaction. The next one, they said which indicator can be used to show the endpoint of a titration between hydrochloric acid and ammonia solution. Now, in order to solve this, obviously we can see very clearly that a strong acid and a weak base is taken as a mixture. And if that's the case, then obviously strong acid and a weak base basically means that the pH range, or the pH range that falls within their equivalence point, is similar to the methyl orange indicator. You can check out the data booklet and check it out. Universal indicator does not provide a sharp color change, so we don't actually use that too much. So the only possible, option, if I talk about the other phenolphthalein, phenol red, methyl orange, you can see that phenolphthalein provides the provides the color change within a pH range which falls outside the change in pH at the equivalence point between a strong acid and a weak base. The same can be said for phenol red. So the only answer was D, methyl orange. Next one is phenolphthalein is very weak acid and it forms a colorless solution under acidic conditions. Sodium hydroxide says is titrated against hydrochloric acid using phenolphthalein indicated at the end point the solution is pink. Now that's because phenolphthalein basically becomes pink. We know that because it becomes basic, right? Now and as acid is, we know that it's a proton acceptor, a base is a proton donor. So a base will be so we can say at the end point it's going to turn pink because the base is basically going to the on the other hand we can say that the not the base actually, so the acid is going to donate the hydrogen ions and it is going to become an anion, as we all know that, right? So um, if that's the case, then the only answer is D right here. Okay. uh, and we know that the weak acid does not accept hydroxide ions under these conditions. So the reason why at the end point the solution is going to turn pink because of phenolphthalein is that the acid here is going to donate the hydrogen ions and it's going to become an anion by itself, in this case the hydrochloric acid. Okay, the next one, they say the dissociation of water in endothermic reaction is this one right here. They told you what is the best estimate of the pH of water at 300 13 Kelvin. Okay, now in order to solve this at 300 Kelvin, we know that 1.0 times 10 to the power minus 14 is provided. Now in order to solve this we can use this process right here. If you use this process, you can see very clearly that the dissociation constant of water is provided right here, 313 Kelvin, and which is given as 2.92 times 10 to the power minus 14. Now we can formulate an equation. We all know that the dissociation constant of water is equal to H plus OH minus. We multiply the product of H plus and OH minus concentration, and at neutrality we know that the concentration is the H plus concentration becomes equal to the OH minus concentration. Then we can easily resurrect the equation, rearrange the equation and give H plus is equal to root KW. So if you find the root of the provided as a water dissociation constant right here, we can easily find the concentration of the H plus ions, and then using this we can basically find the pH of water at 313 Kelvin, which is about 6.77. That approximately sums up to 6.8. So our answer will be C right here. The next one, they said magnesium nitrate decomposes on heating as shown. We can see very clearly. Now this said, what is the expression for the equilibrium constant Kp for this reaction? Now in order to solve this we have to check out what is present in the product side. Normally the partial pressure is normally found for gases, so we can omit the solid product right here. So the only two options are this one, and we also need to check out one thing, that is we need to check out how many moles of NO2 and how many moles of O2 are present. In this case we have half N2, so obviously Kp is going to be the partial pressure of NO2 whole square, and the partial pressure is going to be the partial pressure of oxygen is going to be half, so that the product of these two divided by 1. Why? Because this is a solid and we don't include, like I said, we don't include solid reactant or even solid products when we find Kp, the equilibrium constant Kp. So the our only answer that is logical is A right here. Moving on, we have the next one that says which test can be used to distinguish between each of the pairs of compounds shown. Okay, so if I talk about this one and if I talk about this one right here, we can very clearly see that one contains COOH, the carboxylic acid group. The other basically contains, uh, you know, another one. It's an alcohol. Now, if we warm each compound with Tollens reagent, neither compound is going to react because Tollens reagents only, is responsible for identifying aldehydes, but we don't see any aldehyde group here. if I talk about the next one, if I talk about, D, add phosphorus 5 chloride to each compound, that is also not correct, because we know it is used for detecting alcohol group, and since the alcohol group is also present in COOH, so both are going to eventually react, so we won't be exactly able to distinguish between them, so that's out of the equation, that's out of the equation. If I talk about warming each compound with iodine under alkaline conditions, neither compounds react as well, because both alcohol and carboxylic acids don't react with iodine under alkaline conditions, or even in acidic conditions as well. So that's out of the well. The only possible answer is B. When we add sodium carbonate solution to each compound, they basically react differently. If I talk about if it reacts with COOH, then it's going to produce carbon dioxide, but if it reacts with OH, it's not going to produce carbon dioxide. So that's different. So this is the effervescence is going to take place here, but not here. So this is the reason why you can say that there is the stark difference, the only possible option where we can distinguish between them completely. The next one, they said that we have given with two alcohol groups. One is obviously a primary alcohol. The second one is, I guess, you can say this is an example of a secondary alcohol. Okay. Now here they said that uh, warm the first option, each compound. Now Tollens reagent does not work because they don't have any aldehyde group. Add sodium carbonate solution to each compound, it's not gonna work because both of them contain alcohol groups, so the resulting product is going to be the same, so the observations will be same as well, so that's out of the equation. If I add phosphorus 5 chloride, it's still not going to distinguish between them. The only possible answer, because we know phosphorus 5 chloride is used to identify alcohol groups, and since there is the presence of alcohol group in both compounds, it's not going to be effective. So the only option is C, where we warm each compound with iodine under alkaline conditions. Okay, then it may work. Next one, if I talk about the trial and error method here, right, again, this time things are a little bit different. We can very clearly see that this is a ketone group, and this is an example of very nice aldehyde group. The only possible option I would say is A right here, Tollens reagent, because Tollens reagent will definitely react with aldehyde but not with ketone. So this is the best option for distinguishing between them. A is the correct answer. Next one, if I talk about 11, some thermodynamic information is shown for four reactions. We can see W, X, Y, and Z, and basically all of them react at room temperature. You can see very clearly del H is provided, T del S system. Okay, so the next question is basically about the thermodynamics, or from the energetics chapter. You've got some reactions provided, and they told you which of these reactions are feasible at 298 Kelvin. Now to solve this, we can use del G is equal to del H minus T del S. Now, in order to solve this, we need to ensure that del G, if the del G basically remains positive, so if the del G remains positive, then we can say the reaction is not feasible. But if del G remains negative, then the reaction is feasible. This is the case. We need to ensure that the del G basically remains negative, because if it remains negative, only then it basically becomes feasible. This is known as the Gibbs free energy. If I talk about W negative and with a larger negative value than TWL system, that means this, if this is negative and it's more negative the TWL system, then obviously the whole thing will become negative. So negative basically means what? Negative basically means, as I said clearly before, that the reaction is feasible. So that's in our option. If I talk about X makes del H is negative, so del H is negative. If del H is negative and the T-del system is positive, so eventually the del G is going to become negative, which also makes the reaction feasible as well. If I talk about Y, del H is positive, but T-del system says that it's positive but with a smaller value, positive value than del H, then eventually del G is going to become positive. So we can say that reaction Y is not feasible. And the last one is Z. If del H is positive but T del system is negative, eventually negative negative will result to the addition or positive addition of both the values, resulting to a positive value of Gibbs free energy, making it non-feasible as well. So the only option is B, del W and X, which are the feasible options. They say number 12, they said that which isomer has the most peaks is in its carbon 13 NMR. Now in its carbon 13 NMR, we can see very clearly that we have one, and this one environment to this two environments. And if I talk about this one, and if I talk about this one, so we have two environments, actually three environments right here. If I talk about here, we have one, we have two, we have three, we have four, and then we have a do we have a fifth one? Yeah, we have a fifth one here as well. One and one is same. This one and this one is same in the case of B. This one and this one same. And if I talk about this one, so we have three here, and here we have one, two, three, four, five environments, five different environments. If I talk about this one, then we have six. Uh, so the next one, if I talk about here in B, we can very clearly see that it has only four. It will have four peaks because there is only one, two, three, and if I talk about this one, four. There's going to be four peaks only. So in case of A also, there's going to be only just, if I say so, there's only going to be two peaks because this one and this one are in the same environment, while this one and this one are also in the same environment. So the only correct answer is C right here, because it's going to have different environments, carbon, about six different carbon environments. Anyways, let's move on to the next one. Ethanol and chloride reacts with ammonia. We can see very clearly the reaction is provided. The first step of the mechanism forms the intermediate shown. They said which diagram shows the movements of the electron pairs when ethanamide forms from this from this intermediate. Now we also know that in the what happens during the formation of ethanamide is that this bond, the NH bond, basically breaks down. So the only thing that happens is that the bonded electrons present in the nitrogen atom is get donated to N plus, or the nitrogen atom right here. And in turn, what happens is that we can see very clearly that is the oxygen atom, it tends to donate its lone pair of electrons to the bond right here, so that we can basically release the chloride atom and join with the ammonia. On the other hand, what happens is that the Cl bond basically gets broken down by taking away the bonded pair of electrons, as it's the more electronegative atom right here. So the only rational option, if I talk about others, every other options, the arrow sign is different, indicating signifying a different explanation. So the only rational answer that falls is A, because the arrow signs are provided in the same direction. If I talk about number 14, we have the compound here is shown which reacts with excess lithium tetrahydride to eliminate. They said what solvent is used in this reaction. Always remember that in case of a reducing agent, when it reacts any compound reacts, we basically use ether, or in other words dry ether in this case. So B is the correct answer. The next one, they said what is the organic product that forms. Now obviously we know that whenever we are reducing agent, and we can see very clearly that this is an example of, we can see very clearly this is an example of carboxylic acid. So obviously an alcohol group is going to get produced. So the only option we have here is B and D, but here since it's a double bond, so the answer will be D. The next one, they said which monomer could form a condensation polymer without the needing of a second type of monomer. They said, now in this type of question, when to check out the products provided needing a second type of monomer. Now if I talk about A, you can see very clearly that both uh, functional groups at either side of at either side of the monomer are the same. You can see OH and OH. If I talk about B, the functional groups are not same. But in other words, if I talk about C as well, C is not correct because obviously there's a double bond. So instead of having a condensation polymerization, it's going to go through addition polymerization. So that's not correct as well. The next one is D. Now in case of D, we can see very clearly it's not going to work because one monomer is not going to react with the halogen and alkene on the second monomer. So So only correct option is B, sorry. Only correct option is B, because we have two different functional groups, and a second type of monomer would not be required, for the formation of a condensation polymer. Okay, so with that, our section A is kind of completed. Okay, so we are basically, now let's take a moment to explore the amazing courses we have designed specifically for our January 2025 and May 2025 candidates. On your screen, you will find detailed information about how these courses can help you excel in your exams. So without further ado, let's get started. Moving on, let's start section B. Okay, in section B, we can very clearly see in the first question that in ester X with the molecular formula C8H16O2 has the structure shown. So this is the structure provided. Deduce the name of the alcohol used to synthesize X in a reaction with ethanoyl chloride. Now remember, we can very much clearly see that there are three groups of carbon, and from the ethanoyl chloride, this is the part that comes out. So there is three group of carbons, and we have a methyl group attached with the third carbon right here. So the only option is going to be pentan 3 all, because the carbon is going to get connected, because the carbon is going to be connected with the third carbon right here, while in the third carbon we can see very clearly a methyl group is attached, which is this one. So we can say it's 3-methyl pentan 3-ol is the correct answer. The next one, we see one of the proton environments in X is labeled A. This is the proton environment, and they're saying A is the proton. But complete the labeling of the structure to show each of the other proton environments in X, clearly linking any that are the same. Now, if I talk about this, we have this one as proton environment. If I talk about this, if this is proton environment A, then this is proton environment D, because you can clearly see that the adjacent carbon atom is different, or the environment around this carbon, around the hydrogen protons here is different. If I talk about here, and the protons present in this hydrogen environment are kind of consistent with the one present right here, because both of them are connected to the same adjacent carbon atom. So we can say both of them are in hydrogen environment B. While if I talk about these two carbons right here, this one and this one, we can see the 4 protons are present in the same environment as well, because both of them are connected to the same adjacent atoms. Eventually we get A, B, C, and C, D, 4 different environments to be exact. Now describe 3 ways in which the high resolution NMR spectrum can be used to distinguish between the methyl groups in X other than A. So the other than A, if I talk about the other 3 ones, we have B, C, and D environments. You can check out the chemical sheet for the CH3CO methyl group right here, which is going to be at about 1.6 or 3.0 ppm. You can also check out the CH3CH2. In other words, this part right here. You can also check out the chemical shift of CH to CH2, the alkane group right here, which is going to be about between 0 to 1.88 ppm. You can also distinguish it by checking the peak for CH3CO, which is going to be a singlet, because we can clearly see, we can very much clearly see that the adjacent carbon which it is attached, it consists of no hydrogen atoms attached to it. So according to the n plus 1 rule, 0 plus 1 is going to be 1. So it's going to be a singlet for these three protons right here. If I talk about the next one, the peak for the methyl groups attached to the CH2 group, right here you can see here the CH2 group, they are going to be a triplet. See clearly the adjacent carbon atom right here, this consists of two hydrogen atoms. So obviously basically it's going to be triplet. According to the n plus 1 rule, we have 2 plus 1. The next one we can also identify by using the relative area under the peak for methyl groups attached to CH2 group. Look, if I talk about the relative peak area for the methyl groups attached to CH2 group, it's going to be twice the area under the peak for CH3CO, because we can see very much clearly that there are 6 protons in total, but here there is only 3 protons. So obviously it's going to be double, the proton ratio is going to be double that of the ones present in the CH3CO group. So these are 3 ways we can basically distinguish between methyl groups in X other than A. The next one, an isomer of X, is a carboxylic acid with 5 peaks in its 13 carbon element spectrum. So they told you to draw a skeletal structure for this carboxylic acid. Now obviously we'll draw the carboxylic acid, and since they said there are 5 peaks, there will be 5 different carbon environments. So if you basically rearrange the the diagram of X to like this, we'll be able to get 5 different carbon unique environments. That is the answer. The next one, they said the painkiller aspirin is also used as an ester formed by the reaction of 2-hydroxybenzoic acid and ethanoic anhydride. This is the part of the mechanism as for this reaction, and this is the one we can see very clearly. They told to add a single curly arrow to step 1 and a single curly arrow to step 2 to complete this part of the mechanism. Okay, now in step 1, if I talk about the stuff right here, we can clearly say that we need to check different things right here. uh, so if I talk about step 1 right here, if I talk about step 1 right here, we can very much clearly see that the only option possible here, what happens is that this right here is going to deck. It is basically going to donate this electron to each plus and basically allow it to bond together right here. And then next on, the thing that's going to happen in step 2, they said to step 2, the thing that's going to happen in step 2 is that, as you can see very clearly, see the lone pair of electrons right here. Since one of the bond is going to break by allowing the electrons to get shifted to OH, O here, these electrons is going to get donated and they are going to basically neutralize this bond. So eventually these are the two single arrows that we must add correctly in step 1 and step 2. State the role of the H plus in the synthesis of aspirin. Well, the role basically is pretty simple. It acts as a catalyst. Remember that. The next one, they say this question is about acids containing sulfur, and we can see sulfuric acid reactivates sodium hydroxide solution as shown, and this is the reaction. They told you to calculate the pH when 20 cm cube of sulfuric acid of concentration this much is mixed with 80 cm sodium hydroxide this much. Give your answer in 1 decimal place. At first, we clearly measure the concentration of OH minus as per the volume provided, which is 80 cm cube of sodium hydroxide, by multiplying with the provided concentration. Likewise, we also find the H plus concentration of sulfuric from the sulfuric acid that has come. Then we basically calculate the excess amount of OH minus moles by subtracting it from sodium hydroxide and H plus coming from the H plus of 4, and then we can easily find the concentration by dividing it with the volume provided, which is about 100 cm cube. When we add 20 and 80, that final solution has a volume of 100 cm cube. Eventually we get this concentration. Now as we know POH, we can easily find POH by using this equation, which is this much. We know that pH plus POH is equal to 14, so we can just rearrange the equation and subtract POH from 14 in order to get the required pH, which is 13.2. Next one, they said sulfurous acid, which is a weak acid and dissociates as shown. This is the dissociation reaction. We can see that it says it forms a buffer solution when mixed. State what is meant by the term weak in this context. Now, weak basically means it's an acid solution that contains a significant proportion or amount of undissociated acid. That's right. This is the reason why basically an equilibrium position is reached right down here. The next one, they say, state what is meant by the term buffer solution. That's right. Buffer basically means a solution whose pH barely changes or resists changes in pH when a small amount of acid and when small amount of base or alkalis are added. That's right. The whole point of buffer is that you need to keep this. It helps to keep the solution at a constant pH level, no matter how much acid or alkali you add on it. Next one, they say to calculate the mass of sodium hydrogen sulfate. So at first you basically calculate that should be added 50 cm cube of 0.0408. Okay, fine. Provided using the provided data, we can easily find the H plus concentration right here, which is pretty simple. You can just use this equation right here, and then you can easily get the concentration of H plus. After that, we can rearrange the Kw equation, sorry, the Ka equation right here, like this, and then we can easily find NaHSO3 concentration and find the moles of it, basically, to be honest. Now, after finding the concentration right here, we can find the moles right here like this, because we know the volume is provided. Then we can rearrange the mole by volume formula and then find the moles. Then after finding the moles, using the molar mass provided, we can find the required mass of sodium hydrogen sulfate that must be added. Moving on, we have this question about carbonyl compounds ethanol. Now, ethanol reacts with weak hydrogen cyanide to form a racemic mixture of hydroxynitriles. We can see very much clearly right here. They told you the small amount of sodium hydroxide solution is also added to the reaction mixture. They told to complete the mechanism for this reaction. Okay. Now, in order to complete this is basically the mechanism. At first, what happens, we can see very much clearly that the cyanide group, the nucleophile, attacks the double bond right here. Sorry, the electrophile attacks the nucleophile, the double bond right here, and as a result, the more electronegative element tends to collect the bonded pair of electrons, hence in the process causing a significant breakdown of one single bond. In this turn, the cyanide group gets added, producing an hydrogen intermediate group, and again the oxygen atom gets attacked by the hydrogen group right here, causing the shift of electrons to the cyanide group, and so this bond gets broken down while the H comes here. So immediately this whole process takes place at a fast pace, and this one takes place at a slow pace. This is how basically the whole structure basically reacts. This is the mechanism. Okay, this is an example of an SN1 reaction. The next one, they said explain why a small amount of sodium hydroxide solution is added to the reaction mixture by considering the nature of the attacking species uh, in the slow step. Now, it was basically added to move the dissociation equilibrium HCl to the right in order to increase the concentration of cyanide ions. Because if the concentration of cyanide ions, was added, only then it would have been shifted to the right, because the concentration of cyanide ions here was less, and this would allow the reaction to become more favorable and to so that the reaction can take place and produce this product by this mechanism. Next one, deduce the rate equation for the reaction using the mechanism in A1. Now we can see very much clearly since this is an example of an SN1 reaction, so the nucleophile is obviously going to be involved in the rate equation, so we can say that this is the correct answer. And the next one, sketch a line on the axis to show how the concentration of ethanol affects. There is no change in the concentration of ethanol, so the graph is a straight line like this. Moving on, the next one is that moving on, we can see that carbonyl compounds can be identified from their 2,4-dinitrophenyl hydrogen derivatives. You can see the process right here. The question here says, what are the observations you see in the formation of 2,4-nitrophenyl hydrazine derivative? We'll obviously see a formation of orange precipitate, and the precipitate will be then that's it, outline the steps used to separate and purify the derivative, giving the purpose of each step. Obviously, we'll use a Birchner filtration in order to separate the precipitate, because the orange precipitate right here, if you use Birchner filtration, the efficiency of filtration will be high, because Birchner filtration involves the use of a Birchner funnel, which basically uses pressure in order to separate the precipitate. Secondly, they said what to do and how to purify the derivative. Now we can basically dissolve the impure solid in minimum volume of hot or boiling solvent and then cool it down to form the crystals. Then we can filter and rinse it with ice cold solvent in order to remove the remaining dissolved impurities. This will eventually basically completely purify the derivative of the that we have found from the precipitate. And then we can dry using a desiccator or by keeping it in a warm oven in order to remove the excess water or solvent, whatever you say. Now the only question is, how can we identify the derivative how can we use the derivative in order to identify the original carbonyl compound? It's pretty simple. You can identify the melting temperature and compare it with the data booklet or the chemical literature or the known database, whatever you name it, in order to basically identify the original carbonyl compound. Very simple as that. So however you write it, ensure that these points are available in your answer for this type of questions. The next one, they said the question is about hydrolysis of halogen alkanes with hydroxide ions. So these are the initial rates. We can see that experiment 1, 2, 3. Now they said what state what is meant by the term stereoisomer. Now isomers basically that have the same structural formula but a different spatial arrangement of atoms are known as stereoisomer. Uh, uh, they show that the data in the table are consistent with the SN2 mechanism for the hydrolysis of 2-bromobutane. So now when we know that concentration of 2-bromobutane doubles from 0.15 to 0.30, the rate doubles. So the first order, we can very much clearly see here what is happening. What is happening? We can see when the concentration here is being doubled, we can see what the rate is also becoming double, right? You can see that very much clearly. So if the rate is also becoming double like this, we can see it's becoming double. So if the rate is also becoming double, and if I don't check so this is basically, we can say it's first order, because when concentration is doubling, the rate is also doubling. And so yeah, with respect to 2-bromobutane, it will be first order. Next, if I talk about 2-bromobutane, what is happening here? When concentration of 2-bromobutane is again tripled, we can see right here what is happening. There is an overall increase in the rate of reaction by a factor of 6. We can see the calculation right here. This is over a factor of 6. If you divide it, you get 6. So the change in concentration of 2-bromobutane must have tripled the rate. So the effect of doubling the concentration must have doubled the rates of first order with respect to hydroxide ions. Exactly. So since, as I said, but when the concentration was tripled, the factor increased by 6. So uh, this basically means that the doubling the concentration of hydroxide ion, when we basically double it down right here, what happened? We saw that the reaction basically doubled, right? Yeah, that's how basically the reaction doubled from here to here. So with respect to hydroxide ions, we can say it is a second order. So what does this signify? There are two steps. The first step with first OH minus, basically with respect to 2-bromobutane is first and it's second order, so obviously it's going to be SN2 reaction right here, because the we can, because in SN2 the nucleophile is obviously not involved. Next, if I talk about here, in one experiment a single stereoisomer of 2-bromobutane is hydrolyzed. Explain the stereochemistry of the product for this reaction. Now when 2-bromobutane, we can see very much clearly how is the structure. We can clearly see that this is an example of a chiral compound. So when it basically gets hydrolyzed, obviously the product is going to be optically active, because the stereochemistry, when in another case the chiral center of this 2-bromobutane is going to rotate the plane polarized light in the opposite direction as the bromine atom is very large to attack. Because yeah, we know that the bromine atom, instead of attacking the bromine, the compound that is large, so the hydroxide ion which is coming from the water will not be able to which is coming from the water as a nucleophile is not going to attack the bromine, but it's going to attack from the it's going to attack from the side. It's never going to attack the bromine atom, because the bromine atom is too large to be attacked from both sides of the atom. So you can say that the product remains optically active, because the stereochemistry remain the whole structure basically gets inverted. Okay, the next one we can see that 2-bromobutane 2-methylbutane can also be hydrolyzed with hydroxide ions, and this is the mechanism for this reaction. The reaction profile is shown right here. So they told you explain how all the features of this reaction profile are consistent and with an SN1 mechanism. Obviously we can clearly see that there are two activation energies involved, right? What does it imply? The imply, we can already say that there are two steps in the reaction involved. Two steps, which basically mean that at least in one step we know that SN1 has two steps, right? And one of the step, an intermediate is produced where a carbocation is basically produced, right? Now we can very much clearly see that the activation energy is higher than the previous one as in the second one, which means more energy is required. Hence we can say why more energy is required, because the first step is a slow reaction while the second step fast one. So we can easily say the reaction undergoes SN1 by implying all the clues provided in the reaction profile. Okay, with this our section B is completed. Okay, moving on, let's start with section C. Uh, Number 20. This question is about group 2 compounds. Barium carbonate decomposes at very high temperatures as shown. So we have barium carbonate solid, which is basically decomposed to barium oxide and carbon dioxide as a byproduct. They told you to find the standard entropy change for the system, as we can see very clearly with the data provided right here, with all the standard molar entropy provided for the respective compounds. So the expression for calculation of del system is pretty simple. All you do is that you add, we know that the formula is pretty simple. It is about energy released by the products minus the energy released by the reactants. So that is, using this equation we can just formulate an expression something like this, and we can easily find the del system value. Next up, we can see the lowest temperature which the barium carbonate decomposes provided is 712 degrees. Now using this information you need to answer and use your answer from A1 to calculate the standard enthalpy change of the reaction. Now remember one thing, that is that the minimum temperature for the decomposition of del surrounding theta is equal to the value of the del system which we calculated back here. So the amount of energy produced by this system is released to the surrounding, isn't it? So that basically becomes negative, exothermic in one sense. So, and then we basically convert this temperature provided to kelvins, and then using this equation right here we basically multiply the temperature with the energy provided right here with the enthalpy change of the order del surrounding provided right here, which we, the formula which we are using is del system times T. When we use this formula we can easily formulate this equation and get our values right here, which is 169.3 kilojoule per mole. That is basically the standard enthalpy change of the reaction. Moving on, they said magnesium chloride is used in the manufacture of tofu from soya milk. Now an experiment was carried out to determine the enthalpy change of the solution, and this of anhydrous magnesium chloride. Now 4.26 gram of anhydrous magnesium chloride was added to 200 cm of deionized water in a polystyrene cup. Now the mixture was stirred to ensure all the solid dissolved to form a solution, and you can see that the temperature rose of the solution kind of rose by 6.8 degrees Celsius. They told you to find the enthalpy change of the solution. Now we, whatever the values are provided, we have the specific heat capacity, we know the volume of the solution, and we also know that 6.8 degrees Celsius is the temperature rise. So we can use the formula mc del T in order to calculate the enthalpy energy, amount of energy released which is this one right here. Later on, we can find the number of moles of anhydrous magnesium chloride using the provided mass right here, which is about 4.26, and then we can find the molar mass and then just divide it down to find the mole. After that, we can use our calculated energy released and divide it with the amount of moles which we have calculated in order to find the enthalpy change of the solution, which we can convert it into kilojoule per mole. In order to give it, you can give it in either this size or that size as well, that answer, this form as well, whatever you want. So that's how you basically find the enthalpy change of the solution. Moving on, the standard B enthalpy change of solution. Basically, the anhydrous magnesium chloride, the enthalpy change of solution, the reaction is provided in a Hess cycle format. They told you to complete it. For example, this part and this part. So when basically finding, since they said here and already that this is the lattice energy, in lattice energy what happens is that the production of magnesium chloride right here, what happens is that in the lattice energy reaction, the ions of the constituent elements are found basically react in their gaseous forms in order to produce 1 mole of the ionic compound in the right hand side. So that is the whole format of lattice energy reactions. Whenever we do that, always try to remember that the ions of the constituent elements that make up the ionic compound, which we desire to find, react together in gaseous forms to produce 1 mole of the desired product. Okay, with that, this is our Hess cycle is complete. Moving on, we have the next question that said calculate the enthalpy change of hydration of chloride ions using the cycle and data. Now, if you use this cycle, we can easily find the hydration of the chloride ions. We can just easily find it out. What we did down here was pretty simple. We knew that our value of enthalpy change of the solution, which of this one right here, this value we knew it was 127 kilojoule, and then we had the lattice energy, which was this much. So what we did is we added the lattice energy, and then we basically went clockwise. So we added the lattice energy, added this enthalpy change of solution, and we also went upwards. So what happened is that in the left hand side it was supposed to be 920, but when we brought it back to the right hand side it became negative, along with the hydration energy of chloride ions right here, because only the enthalpy change of the magnesium ion was provided. So this was supposed to be found. So we found that, which was about negative 77333. Now that's for 2 chloride ions. If you just divide it by 2, we'll be able to get for individual ones. That is what we are supposed to find. So that's the answer. The standard enthalpy change of hydration of chloride ions. Moving on, the theoretical lattice energy for magnesium chloride is negative 2326. They told to give 2 assumptions used in theoretical calculations of lattice energy. Now remember one thing, that 2 theoretical assumptions that you might want to say. They says the bonding is 100% ionic and the ions are in contact with each other. Well, that is not the case. In ideal scenario it must be, but in real-time scenario it isn't. There are some covalent characters as well, which cannot be avoided, and ions in real time are not in contact with each other, to be honest. But since they said assumptions which are only found in ideal scenarios, so we can basically assume these are the 2 things that must be in an ideal scenario. Okay, the next one, they said explain the difference between theoretical and experimental values for the lattice energy of magnesium chloride. Okay, fine. So the lattice energy, we can see the experimental value which we have calculated. It was more exothermic, right? Because it was negative, as you can see very clearly. So why was that the case? Because the chloride ion, it got polarized by the magnesium ion. So this basically gave the bonding in the magnesium chloride some covalent character. Hence, this made the bonding much more stronger. So the covalency basically increased strength of the bonding overall. So that's just like I said, Even though this is an assumption, the bonding is 100% ionic. This is not the case, because in real time, as you can see very clearly, due to polarization of the cations, of the cations, to the anions, have basically, gives rise to covalency character in this type of compounds, mostly ionic compounds. Okay. Okay, so the next one, if we move on, hydrated barium chloride is a soluble toxic salt. It can be formed from the reaction of barium carbonate with hydrochloric acid as shown. Now, this is the reaction provided. A 5-gram sample of barium carbonate reacted with 120 cm cube of this much concentration of hydrochloric acid. They told you to show the hydrochloric acid is in excess. Is in excess in this reaction. It's pretty simple. What you can do is that you just need to show it, right? So at first, let us find that the number of moles of barium carbonate. Now, we know that 5 gram of barium carbonate reacted, so you can just divide it with its molar mass and find the number of moles, and then you can also calculate the moles of hydrochloric acid. So as you can very much clearly see, now since there are 2 moles, you have to divide it by 2 in order to get 1 mole. So as you can see very clearly, that is 0.03, and that 0.0234 is the barium carbonate moles. That's basically less than the amount of provided HCl required to react. So we can say that the HCl, by seeing the values of the moles of HCl and barium carbonate, we can easily say and prove and show that the hydrochloric acid was indeed in excess in this reaction. The last question of section C, which says all of the barium carbonate reacted and produced 6.19 gram of hydrated barium chloride. They told to calculate the relative formula mass of barium chloride NH2, hence deduce the value of N. Now this is pretty simple. At first we basically calculate the moles of barium carbonate, which is basically kind of equal to the moles of barium chloride here as well, because as I said, it is a one as we can see very much clearly, it is a 1:1 ratio. You can see that, right? 1:1 ratio. So if you can find the barium chloride moles, which you can easily do by just provide dividing with the molar mass with 5 as provided in the sample, so that's the amount of moles which is equal to the barium chloride. So we can easily find the molar mass of uh, barium chloride right here. So we can just do that. We found that is the molar mass of barium chloride, hydrated barium chloride to be exact. And now we can just do what? We know the total molar mass. We can just omit the remaining part. We can just omit the remaining BCl2 part and BCl2 part in order to get the mass of water. And after getting the mass of water, we can divide it with the molar mass of water in order to get the number of moles of water actually present. So that is 2. So the value of N, which actually represents the number of moles of hydrated crystals present in this salt, is 2. So that's how you basically calculate. Anyways, that's it for this video. I hope you like, share, and subscribe exam essential videos. uh, make sure to click the bell button and for getting regular updates and question papers solving sessions. We'll be solving more at the future. For today, bye.